Welcome to this explainer on the foundational language of precision engineering. Today, we are solving the ultimate manufacturing mystery. Why do parts pass inspection on paper but completely fail on the assembly floor? By the end of this, you'll know exactly why engineers who actually understand this language get parts right the first time, and why the ones who don't are just doomed to keep reordering expensive scrap.
Picture this scenario. A beautiful, incredibly expensive machined part just arrived on your desk. Quality control measured it, and every single dimension falls perfectly within its plus or minus tolerances. It passed. Everyone signed off on it. But then, you take it down to the assembly floor, you try to slide a bolt through it, and it just doesn't fit. The part is useless. So, what exactly went wrong?
Well, take a look at this stark comparison. On the left side, you've got traditional coordinate tolerancing, just your standard ambiguous plus and minus limits. Now look at the right. That is the exact same part, but it's defined with GD&T, using geometric precision constraints. I want you to ask yourself right now, which one of these actually guarantees the part is going to work? The one on the left leaves massive room for interpretation. The one on the right, it leaves absolutely nothing to chance. And look, we're not just nerding out over abstract geometry here. We're talking about real bottom-line dollars. That ambiguity you get from traditional tolerancing, it's a $10,000 mistake just waiting to happen. Relying solely on plus-minus limits is a huge financial drain. It causes ballooning scrap rates, endless cycles of rework, and incredibly bloated inspection times, while your team tries to figure out why a quote-unquote good part won't actually fit together. Enter the solution. The ASME Y14.5 standard. This is the engineering product definition standard. Think of it as the ultimate internationally recognized rulebook. It's the definitive guide that takes all that manufacturing ambiguity and replaces it with absolute mathematical certainty. To truly master this rulebook, we have to start by nailing down one fundamental distinction. What is the difference between a dimension and a feature? A dimension is literally just a number. It's stating that a clearance hole must be exactly 6.44 millimeters in diameter. A feature, on the other hand, is the actual, tangible, physical geometry itself. To make this super concrete, we're going to follow a simple metal bracket with a clearance hole as our running example for this entire masterclass. Let's watch how that old ambiguity guarantees real-world failure for our bracket. Step 1. The engineer designs the bracket with a standard plus-minus tolerance for the hole size. Step 2. The machinist makes the part, cutting it right to the absolute edge of that tolerance limit. The caliper says it's technically the right size. But step 3, out in the real world, the actual axis of that hole varies obliquely. It's tilting completely out of perpendicularity with the surface. So by step 4, when you drop the fastener in, it fails to clear. The dimension was right, but the physical feature failed. This is exactly where GD&T flexes its mathematical muscles. Straight from Appendix B of the standard, we have the floating fastener case. The formula is beautifully simple. H equals F plus T. That means the clearance hole minimum size must equal the fastener maximum diameter plus the positional tolerance. By defining the tolerance of the actual geometry's position, not just the size of the hole, GD&T mathematically guarantees that bolt will fit into that bracket every single time. So we know it works, but here is the exact part where most engineers get it completely wrong. Time for a quick pop quiz. If we're applying a position tolerance to our bracket's hole to make sure the bolt actually drops in, which of the major geometric categories does that position symbol belong to? Think about what it's physically controlling on the part. Well, if you guessed location, you absolutely nailed it. The crucial point here is that position falls squarely under the location category. It controls exactly where a feature is located in space relative to your datums, not just how big or small the drill bit was. This is the exact constraint that prevents that dreaded oblique drift we saw ruin our bracket earlier. This framework right here is your ultimate roadmap for the rest of this series. The standard outlines 14 primary symbols, and they are grouped into 5 strict categories. You've got form, which controls the shape of a single feature, orientation for managing angles relative to a datum, location, which we just tackled, profile for dictating the outline of complex surfaces, and runout, dealing with variation during rotation. Keep this mental map handy because we're going to be referencing it heavily, especially when we get into the truth about runout in Lesson 4. Now, once you've got these fundamentals down, it gets really exciting. Take a look at these advanced applications straight from the standard. Composite positional tolerancing. This literally allows you to control massive patterns of features, like a huge grid of bolt holes, by constraining both the pattern locating zone and the feature relating zone all at the exact same time. It might look like a lot of heavy math right now, but I promise you, it's just the natural evolution of the core language we're learning today. So let's stop guessing, all right? Stop just hoping parts will miraculously assemble. It's time to start speaking the language of precision. Engineers and inspectors who understand this geometric framework completely eliminate ambiguity. They crush their scrap rates, and they design parts that work exactly as intended, straight off the machine. Think about it. If one ambiguous tolerance callout can cost you 10 grand in scrap, what is your current blueprint language actually costing your operation right now? You know why GD&T is critical, but can you actually read it in the wild? In Lesson 2, we're going to crack open the exact compartments of a feature control frame. By the end of it, you'll be able to instantly decode the tolerance zone, the shape modifier, and the datum references of any blueprint like an absolute pro. See you there.